Welcome to geology again, folks. Here we go with the next three. So you should have already made it through the two divergent boundaries. Now we got to look at what happens when plates come together at convergent boundaries. And there's going to be three types of those, so we got to do three videos for that. So we'll start with the first one arbitrarily. The first one, because I think it's the easiest way to explain it, would be what's going on over here. So let's rewind to what you did in the last video. The red line here is divergence, oceanic. So this plate is being essentially created, born right there, and then spreading out that way, eastward. And likewise, spreading out that way, westward, opening up, right? That makes this tectonic plate right here, all of which is going and slamming into South America. And what's going on here? And what is the result? You can kind of see it right there. If I turn this off, you can see this black line right there. So this is an like observable one, even without the idea of tectonics in Google Earth, right? Given the right technology, the right ability to scan the ocean floor, you can really make that thing out right there. What's going on with this dark line? And I bet you depth-wise, yeah, if you follow down here in the corner, the depth, it's shallow near the coastline, obviously. It gets deeper, and it's deepest right around there, and then gets shallower and shallower and shallower as you come out. So what is that thing, and what is this mountain chain right through here? All of those are results of this boundary that we're about to discuss, which is convergent. This plate and this plate are converging with each other, coming together. And then I call it OC in the notes, which stands for oceanic continental. So the two different kinds of plates are going to come into play here. We talked about it back when I did like rifting and talked about this. I said there's thicker continental crust and thinner oceanic crust. At that point, it was kind of like, okay, that's the way it is. Over here, it's really critical to see that the thinner crust and the thicker crust interact with each other and figure out what goes on. So let's do it. So convergence, and in the notes again, it says OC, which stands for oceanic continental. Let's draw it. Here's approximately what it should look like. We're going to have thinner oceanic crust. Let's go with thinner pen here. If that ridge system is over here, MORS for mid-ocean ridge system, right? If that's back there off my page a little bit, and again, just to throw it out there, that's what this red line is mid-ocean ridge system. This oceanic crust is moving that way. So I'm going to draw a little arrow inside it to say this. Now, the idea that it's thin is in this diagram, and it's important. So it's going that way, and it has the Pacific Ocean on top of it. Right? What happens when it runs into a continent? When it runs into a continent, that crust, which I'll draw over here, is thicker. Now, I'm also going to throw at you some ideas with density. Although this oceanic crust is thinner, it's more dense. And though this oceanic crust is thicker, it's less dense. And what that leads to is there's this idea of isostatic balance. If this part down here in the asthenosphere is kind of mushy, not a liquid, but a mushy solid, and things are going to sink into that the way you do in a mattress, the thicker, less dense one and the thinner, more dense one have some sense of isostatic balance, right? So what's going to happen when they come together? Since this one's more dense, it hits the thicker, more buoyant, less dense oceanic crust and gets sucked down underneath. All right, we call this process subduction. What's left, and I probably should have those touching a little bit. What's left here is that this thick part, this where they're dragging each other down, right there, is going to be a trench. And that's what we spotted in Google Earth there, that dark line where it's extra deep. That dark, and the blue one's superimposed right on top of that. Again, if I get rid of it, that dark line is the trench where the oceanic plate is being sucked underneath the continental plate. And as it happens, it like drags down on it and makes a deeper part right about there. All right, this is going to lead to a couple of things happening. One, there is going to be some pressure on the crust here. As this gets rammed into by this oceanic crust, it's going to be compressing. And when rigid things compress and start to crack, we're going to start to get some tectonic activity. And that's been responsible for some like shortening of the crust. And when that happens, not only does it shorten, but it gets thicker. If you're mashing it together the way you would, I don't know, push snow together, push clay together. If you push it together, it's going to start to thicken. So I'll draw some little like ridges in here to say that that goes on. And what that'll start to do is uplift some mountains here. Another thing that happens is that you get to a point down here. Oop, somebody at my door. One moment. Sorry about that. So we got subduction happening here, dragging this crust down, where getting deeper within the asthenosphere, it's going to be warmer and warmer and warmer. Also, as part of what's going on, I'm going to finish my ocean here. As part of what's going on with the ocean and with the way this rock was formed, there's going to be water like as part of the chemical makeup of this rock. And that's going to get driven off at heat. And between that and the increased pressure and the increased temperature, it gets a little complicated down there. I think more complicated than we need to get in a 100 level course. But maybe say we're 100 to 150 kilometers down there, we're going to start to get some melting of the crust. And when it's hot and it's liquids-ish, it starts to rise up. And I'm drawing these are like upside down teardrop shapes. That's kind of how they look as they melt their way up. We'll call them magma plumes. I'll note that here. Those little teardrop shaped guys will be called. So they can work their way up. Some probably cool within the crust, lead to igneous rocks we may find later when all this erodes. But some of them are going to work their way right out the surface. And when magma comes out the surface and we call it lava, we say, hey, there is a volcano. Now we'll look at types of volcanoes as another part of this. I don't want to overcomplicate life too much right there, but we're certainly going to just say volcanic mountain chain is really the results of these kinds of situations. That'd be the landform. If you're doing those notes, that's the landscape that you get. There's a trench and volcanic mountain chain. Let's just look at it one more time quick in Google Earth. And that's what we got here. It's called the Andes. Volcanoes. Let me see if I can find my volcano layer. Okay, found it. So the result again, volcanic mountain chain. If I turn on volcanoes of the world, all these little rectangles are they. All right, so can you see this diving down, going underneath, melting, and creating all this? Again, it's tricky if you're not like feeling really great about cross sections, but this is what it would look like if you were to cut the Earth and look at it from the side. Google Earth essentially is what would it look like if this is my eyeball way higher, the view that I have looking down. What do I see? I see this volcanic mountain chain. I see the bottom of the ocean, a trench, and then I see the rest of the Pacific Ocean and that. What do we see from the side is that diagram, right? I think that should just about do it. What do you think? I like it. So next will be what happens when we get an oceanic and an oceanic. We'll do that soon. Thanks, everybody.